Hi everyone. We are going to continue today to talk about derivatives of exponential and also logarithmic functions today. So last class we looked at this function, f of x equals e to the x. I'm going to switch to black. And we saw that f prime of x also equals e to the x. Okay, so we looked into why that was, and then we practiced finding the derivative of functions where the base is e. And today we're going to look at a couple of other exponential functions and also some logarithmic functions on top of that. And the reason why we started with the function f of x equals e to the x is that all of the derivatives of the other functions are based on this one. And so the first function that I'd like to start with is this one, y equals ln x. And remember that when we're looking at ln, that's the natural logarithm. That's the same as a log with a base e. Okay, so what I'd like to do to figure out the derivative of this function is actually switch this into exponential form. So if we do that, then what we're going to have is that the base of our exponent is e, the exponent is y, and the value is x. So that's what this function would look like in exponential form. Okay, and we're going to differentiate this instead because we know what the derivative of e to the y is. Okay, so we're going to be looking at some implicit differentiation here. So if we take the derivative of the left side, well, the derivative of e to the y is just e to the y times dy dx. And the derivative of x is 1. Okay, now we can do a substitution though, because e to the y equals x. So I can take this and sub it in here. So what I'm going to get is that I'm actually going to get x times dy dx equals 1. And then I can divide both sides by x. Whoops, there we go. And I end up with dy dx equals 1 over x. And that is the derivative of the function y equals ln x. Okay, so therefore, if y equals ln x, y prime equals 1 over x. And this is another derivative that you will not be given. You need to know this one. It's not on your formula sheet. Okay, so that's the first one that I wanted to start out with. Okay, and we're going to look at two others before we practice using them. So the next one, and this is a logarithmic one, by the way. The next one that we're going to look at is an exponential function, but now the base is not going to be e. It's just going to be for an exponential function with any base. Okay, so maybe I'll start here. Okay, so let's say we have the function y equals b to the x, and b can be anything. So I'm going to do some, algebraic gymnastics, as I like to call it here. And I'm going to replace the base b with e ln b, because these are equivalent to one another. And if you want to know why, then we can see why if we change this into logarithmic form, right? Logarithmic form, well, we're going to have a ln, because the base of the exponent is e, so we have to have a logarithm with base e. The argument is going to be b, which is this guy, because that's the value of the exponent, and that has to equal the exponent over here, which is ln b, right? So that's why b is equal to e to the ln b. And in order to take the derivative of y equals b to the x, we're going to do this substitution. So I'm going to take this and sub it in for b. And the reason why I wanted to do that is because now, but the base is e, we actually know how to take the derivative. Okay, now we're just essentially looking at the derivative of f of x equals e to the x with a chain rule. So y prime is going to be e to the ln b times x times the derivative of this exponent, right? And the derivative of the exponent is ln b, because ln b is just a constant, right? Because the value b is a number. Now, this is equal to e to the ln b to the x times ln b. And now we can sub b back in for e to the ln b, which is just b to the x times ln b. So that is the derivative of this original function. If y equals b to the x, y prime equals b to the x times ln b. Okay, now this one will be given to you on your formula sheet, so that is not one that you need to memorize. Okay, and then the final one that I want to look at is a logarithmic function where the base is not e. We're just looking at a log with any base. So let's say we have y equals log base b of x. Okay, so what I'm going to do here is I am going to, again, switch this into exponential form, just like we did when we were looking at the first derivative that we looked at, which was y equals ln x. And when I switch this into exponential form, what I'm going to get is base is b, the exponent is y, and that's equal to x. Now, if I take the derivative of both sides, differentiate this, I'm going to do implicit differentiation again. Well, the derivative of the left side, based on what we just did for the second one, is going to be b to the y times ln b times dy dx. And that's going to equal to the derivative of x, which is 1. Okay, now b to the y is equal to x, so I can take this and sub it in here. So that's going to equal x times ln b times dy dx, and that's equal to 1, which means if I divide both sides by x times ln b, then I will isolate dy dx. Okay, so this is the derivative of the function y equals log base b of x. All right, so now I'm going to return to the notes. Or actually, I'm just going to go to the notes because I don't think I went to the notes yet in this video. Here we are. Now, at the top of the notes, you have all of these different derivatives. Okay, so we just went through these three, where these come from. Okay, these two are on your formula sheet. Okay, the first one is not. You need to know that. The other three just beside them, honestly, I never memorize those or remember those. These are just the ones to the right of them, or sorry, to the left of them with the chain rule applied. Okay, so has been applied. So if you know how to use the chain rule, you don't need to know all of this stuff. You just need to know the three on the left, and you need to know how to use the chain rule. And we'll look at what that looks like down below. Okay, but really you need to know the three on the left, and specifically you need to memorize the one at the very top. If y equals ln x, y prime equals 1 over x. Okay, so we're going to practice doing this. Now, this first function, y equals x times ln of 4x squared minus 7. So we're going to have a chain rule in here because we've got the ln of 4x squared minus 7. But then we also have a product rule because we're multiplying that by x. Okay, so our u equals x, which means our u prime is equal to 1. Our v is ln of 4x squared minus 7, which means our v prime is, well, it's going to be 1 over whatever we're taking the ln of, which is 4x squared minus 7, times the derivative of whatever we're taking the ln of, which in this case is 8x. Okay, or it's 8x, whoops, didn't want to do that, 8x over 4x squared minus 7. Okay, so putting this all together, y prime is going to be u prime v. So that's 1 times the ln of 4x squared minus 7 plus uv prime, x times 8x over 4x squared minus 7. Okay, and all together, if we just simplify that a little bit, it is ln of 4x squared minus 7 plus 8x squared over 4x squared minus 7. Okay, so there is our first example. In our second example, here we have to use our chain rule because we're looking at y equals ln of another function. Okay, so again, chain rule here. Okay, so y prime, and actually before I do that, I would write this as the ln of cos x squared. Okay, so y prime is going to be 1 over whatever we're taking the ln of, which is cos x squared, times, well, we have to take the derivative of the something squared, which is 2 times that something to the 1, which is cos x to the 1, times the derivative of that something, which is negative sine x. So actually we have to apply 2 chain rules here. Okay, now one of the cosines in the numerator, or the cosine in the numerator rather, cancels with one of the cosines in the denominator. So we have some simplification that goes on. This will cancel with one of these. And so we're going to end up with, in the numerator, negative 2 sine x over cosine x. And remember, sine x over cosine x is tangent x. So we're going to end up with y prime equals negative 2 tan x. And that is our derivative. Okay. C. All right, so we've got the ln of the square root of x over x plus 1. Now, we could treat this as a single logarithm. And that would be kind of a yucky chain rule to deal with, right? Because we'd have to take the derivative of the square root of x over x plus 1, which is not very fun. But remember that we can also use our laws of logs. And so we can actually rewrite this function as the difference of 2 logarithms using the quotient rule. And this is going to be something that's much easier to differentiate than if we had done it as a function with only one logarithm. Okay, and actually remember that the square root of x is like x to the 1/2. So I'll just do that as well. Okay, now y prime, from the first logarithm, it's going to be 1 over x squared. Sorry, not x squared, my bad. 1 over x to the 1/2 times the derivative of x to the 1/2. So that's 1/2 x to the negative 1/2 minus 1 over x plus 1 times the derivative of x plus 1, which is just 1. Okay, now we have to simplify this a little bit. So from the first term, the x to the negative 1/2 is going to come down. We're going to get 1 over 2 times x to the 1/2 times x to the 1/2 minus 1 over x plus 1. And that is just 1 over 2x minus 1 over x plus 1. Okay, now we can write that as a single expression, right? We can subtract those two expressions with a common denominator. So we're going to get y prime, and that common denominator is 2x times x plus 1. And the first one we need to multiply by x plus 1, so that's going to be x plus 1. And then minus the second one we need to multiply by 2x. Okay, and then we can simplify that. So in the numerator, x plus 1 minus 2x, so that's x minus 2x is negative x. So 1 minus x over 2x times x plus 1. And that is our y prime. All right. Okay, so let's try a couple more of these. Here we've got, for D, we're going to have to do some implicit differentiation. And we also have like an exponential function in there as well. So D, whoops, I got to turn my pen on. D by dx of x is going to equal d by dx of y squared plus d by dx of 4 to the x. Okay, and d by dx of x is just 1, and that's going to equal d by dx of y squared is 2y times dy dx. And then d by dx of 4 to the x is 4 to the x times ln 4. All right, and now we have to just go about isolating dy dx. So maybe I'll like subtract 4 to the x ln 4 from both sides. So I'll have 1 minus 4 to the x times ln 4 equals 2y rather times dy dx. Okay, and then to isolate dy dx, I just have to divide both sides by 2y. So I'm going to get dy dx equals 1 minus 4 to the x ln 4 over 2y. And that's my derivative. Okay, and for E, I have here an exponential function and a product rule. And it looks like I have a chain rule as well. Lots of stuff going on. I'm going to start with my product rule. Okay, so u is x, u prime is 1. V is 10 to the x squared minus x. V prime is going to be 10 to the x squared minus x times ln 10 times the derivative of x squared minus x, which is 2x minus 1. Okay, so putting this all together, y prime equals u prime v, so 1 times 10 to the x squared minus x plus u v prime, x times 10 to the x squared minus x times ln 10 times 2x minus 1. And then actually I have a common factor of 10 to the x squared minus x, so I can factor that out. And in the first term, I just have a 1. And in the second term, I've got lots of stuff. So let's see, I've got ln 10x times 2x minus 1. And I think I'm going to stop there. Okay, so that's my y prime. I suppose I could keep going and distribute the ln 10x into the 2x minus 1, but I'm going to stop there. All right. Okay, so now we're looking at logarithmic functions where we do not have base e. So this is y equals log base 3 of x cubed plus 2x. And remember that if y equals log base b of x, then y prime equals 1 over x ln b. Okay, so that's from the previous page, and also we derived that at the very beginning of this lesson. If y, well, I'll just turn on my pen, y equals log base b of x, then y prime equals 1 over x ln b. Okay, so we have to kind of remember that. Remember, you can have your formula sheet out when you're doing these, so you don't have to memorize that one. Okay, so, and we have a chain rule in here, of course, as well. Okay, so y prime is going to be firstly 1 over whatever we're taking the log of, which is x cubed plus 2x times ln of the base of the logarithm, which is 3, times the derivative of whatever we're taking the log of, which is 3x squared plus 2. And I can simplify that a bit. It's going to be 3x squared plus 2 over ln 3 times x cubed plus 2x. Okay. And then the next one's similar, but we're adding in a product rule. So we've got, okay, u equals x, u prime equals 1, v equals log of x squared, v prime equals 1 over x squared times ln, remember if there's no base written into the logarithm, it's base 10, so ln 10, times the derivative of x squared, which is 2x. All right, so let's put that all together. So y prime is going to be u prime v, 1 times log of x squared plus uv prime, x times 2x over x squared ln 10. Okay, and then we can simplify the second term, because in the numerator we've got 2x squared, and in the denominator we also have an x squared. So this second term is actually just going to be 2 over ln 10. It's like a constant. Okay. And then finally, we have this last question. Where is y equals ln x over x increasing? Okay, so this is kind of like one of those curve sketching questions, right? So where is it increasing? When y prime is positive. Function's increasing when the derivative is positive. So we need to take the derivative, find the critical numbers, and figure out from those critical numbers which are the regions in which the derivative is positive. Okay, now another thing you need to consider about this function is that when you're taking the logarithm of a number, you can only take the logarithm of positive numbers. So for this function, x must be greater than 0. And actually it can't equal 0 because we're dividing by x in the denominator, right? So if it was just y equals ln x, then x could equal 0 as well. But because we're dividing by x, x has to be just greater than 0. Okay? So we're going to keep that in mind as well. All right, so now for our quotient rule. We got to use a quotient rule here because we're dividing two functions. So we've got u equals ln x, u prime is 1 over x, v equals x, v prime equals 1. Okay, so for our derivative, y prime is u prime v, 1 over x times x minus uv prime ln x times 1 over x squared. And that works out to be 1 over x times x is 1 minus ln x over x squared. Okay, so that's our derivative. Now, if we want to know what are the critical numbers, right, if we set this equal to 0, okay, well, obviously 0 is going to be a critical number because that's when the denominator is equal to 0. But we've already spoken about that. We've kind of addressed that through the domain, right? Here's 0, and this part of the number line is gone. We're not considering that. So we really need to find the critical number, solve this equation, 0 equals 1 minus ln x, which means I'm kind of running out of space here, but ln x equals 1. Okay, now to solve this, you need to think about exponential form. The base of this logarithm is e. So if we switch this into logarithmic, or into exponential form rather, we're going to have base e to the exponent 1 equals x, which means that x equals e. So our critical number is e. And we basically need to think about, is the derivative positive or negative in these two regions? We've got one region from 0 to e and another region from e to infinity, right? We want to know the sign of the derivative. Now, knowing that the derivative has an x squared in the denominator, I really only care about the sign of 1 minus ln x because x squared will always be positive. So from here, I may test in this region. E, remember, is about 2.72. So I may test something like 1 minus ln of 1, for example. And if you plug that into your calculator, then you'll find that that is a positive value. And here, if you plug in, let's say, 1 minus ln of, I don't know, 5, anything greater than 2.72, you'll see that that's negative. So to answer the question, where is the function increasing? The function is increasing between 0 and e. All right, so I'm going to end it there for today, and I will see you guys again soon.